In this video, we're going to look at finding limits of the following sequences. Part A, an is equal to log n squared divided by 2n. Part B, bn is equal to 1 plus 1 over n to the power of n. Part C, cn is equal to 2 to the n divided by n factorial. Part D, dn is equal to negative 1 to the n times n to the 2/3 divided by n to the 2/3 plus 3n. And part E, en is equal to n minus square root of n squared minus 3n. In all of these 5 questions, we have to find the limit of the sequence as n goes to infinity. Let's look at part A. So we have an is equal to log n squared divided by 2n. Notice that the numerator, log n squared, approaches infinity, increases to infinity as n goes to infinity. And the denominator 2n also approaches infinity, becomes increasingly larger and larger as n goes to infinity. That suggests that we should use L'Hopital's rule because we have the infinity over infinity pattern. So since log n all squared divided by 2n has infinity divided by infinity pattern, we're going to apply L'Hopital's rule. L'Hopital's, let me get this spelling right, L'Hopital's. All right, so let's make the function f of x is equal to log x squared divided by 2x. Now let's take the limit as x goes to infinity, log x squared divided by 2x. So we're going to apply L'Hopital's rule. We differentiate at top and we get 2 times log x, applying the power rule and the chain rule, multiplied by the derivative of the inside. Derivative of log x is 1 over x. Now differentiate the bottom, differentiate 2x and we get 2. So the result is going to be 2 log x times 1 over x divided by 2. And we should put limit as x goes to infinity on all these expressions. So limit as x goes to infinity. The 2's cancel out. So what we have is limit as x goes to infinity of log x divided by x. But this is still infinity over infinity because log x is an increasing function of x. As x goes to infinity, log x goes to infinity. Log x goes to infinity. And the denominator x also goes to infinity. So we have infinity over infinity pattern. We apply L'Hopital's rule one more time. So we take the derivative of the numerator, and derivative of log x is just 1 over x, and derivative of x is just 1. Now taking the limit as x goes to infinity of 1 over x, this is equal to 0. So what we have shown is that the limit as n goes to infinity of an is equal to limit as n goes to infinity of log n all squared divided by 2n. The limit of this sequence is 0, and we achieve this by applying L'Hopital's rule because we had the infinity over infinity pattern. So our conclusion is that the sequence an is equal to log n all squared divided by 2n converges to 0. It has a converging limit of 0. Converges to 0. All right, let's look at part B. For part B, let's take the limit as n goes to infinity of bn. This is equal to limit as n goes to infinity 1 plus 1 over n to the power of n. Notice we have 1 over infinity, which is 0. 0 plus 1 is 1. So we have the pattern. The pattern is 1 to the infinity. So this is an indeterminate form. We're going to apply the log function to change this pattern from 1 to the infinity to 0 divided by 0. So we can apply L'Hopital's rule. We're going to let y be equal to 1 plus 1 over x to the power of x. Now log both sides, we get log y is equal to log of 1 plus 1 over x to the power of x. And because of the property of log, the exponent comes down. We get x times log of 1 plus 1 over x. Now let's take the limit as x approaches infinity of log y. This is equal to limit as x goes to infinity of x times log of 1 plus 1 over x. This is equal to limit x goes to infinity log of 1 plus 1 over x divided by 1 over x. Now, if we look at the pattern, is 0 over 0. Why is that? If you plug x equals infinity, you get 1 over infinity, which is 0. 0 plus 1 is 1. We get log of 1 in the numerator, which is 0. And in the denominator, we have 1 over infinity, which is also 0. So we have 0 over 0 pattern, which means, and of course the reason is because log of 1 plus 1 over x goes to 0, and 1 over x also approaches 0 as x goes to infinity. So we're going to apply L'Hopital's rule to log of y. So limit as x goes to infinity of log y is equal to limit x goes to infinity of log of 1 plus 1 over x divided by 1 over x. Now recall with L'Hopital's rule, we take the derivative of the numerator and divide by the derivative of the denominator and take the limit. So we have limit x goes to infinity. Differentiating the numerator is going to give us 1 divided by 1 plus 1 over x. Applying the chain rule, differentiate the inside of the brackets, and we get derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. And now differentiate the denominator. The derivative of 1 over x, applying the power rule, 1 over x is like x to the minus 1. So differentiate, you get negative 1 x to the minus 2, which is negative 1 over x squared. Well, that's good because we get a nice cancellation here. Negative 1 over x squared cancels out. And we get limit as x goes to infinity of 1 divided by 1 plus 1 over x. Now this is going to be just 1 because 1 over x will approach 0 as x goes to infinity, so we get 1 over 1, which is 1. But we have to remember this is the limit of log of y. So to get the answer, we have to exponentiate log of y. X goes to infinity is equal to 1. Exponentiate both sides, we get limit x goes to infinity of e to the log y is equal to e to the 1. So we get limit of y as x goes to infinity is equal to e. But remember, y is equal to 1 plus 1 over x. Y essentially is our sequence, except we wrote it in terms of a real variable x, so we could apply L'Hopital's rule. So we have limit as x approaches infinity of 1 plus 1 over x to the power of x is equal to e. Well, that means that the limit as n goes to infinity of 1 plus 1 over n to the power of n is equal to e. That means this number e is actually the limit of a special sequence, namely this sequence, 1 plus 1 over n to the n. So what we have shown is the sequence Bn is equal to 1 plus 1 over n to the power of n converges to 0. Sorry, converges to e. Converges to e. That's the special, essentially the special number e. And if you write out a few terms, you'll get a feel for this. For example, if you have n equals 1, you'll get 1 plus 1 over 1. That's going to give us 2. 1 plus 1 half, that's 3 half. 1 plus 1 third. And let's say 1 plus 1 over 1,000. Of course, these are all raised to the same power, 1,000. This is raised to the power of 3. This is raised to the power of 2. So if you put this in the calculator, you'll see it actually comes out to be very close to the number e. So 1 divided by 1,000 equals plus 1. Let's put this all in brackets like so. So let me write this better. We have 1 plus 1 over 1,000, all to the power of 1,000, and this sequence goes on forever, of course. So we have 1 divided by 1,000 equals plus 1 equals y to the x 1,000. We get 2.7169, pretty close to the number e. So this is an idea of why sequences are important, because we have shown that the number e is actually the limit of a special sequence, which is 1 plus 1 over n to the power of n. Now let's look at part C. Part C, we have Cn is equal to 2 to the n divided by n factorial, where n factorial is equal to 1 times 2 times 3 all the way to n. All right, so let's write out a few terms. C1. C1 is going to be 2 to the 1 divided by 1 factorial. C2 is going to be 2 squared, which is going to be 2 times 2, divided by 2 factorial, 2 times 1. And in general, Cn is going to be 2 to the n, so 2 times 2 n times 2, divided by n factorial, which is 1 times 2 times n. All right, so it looks like the fractions that we're looking at are decreasing as the denominator grows faster than the numerator. So let's rewrite this. Rewrite this as Cn is equal to 2 over 1 times 2 over 2 times 2 over 3 times 2 over 4 times 2 over 5 times 2 over 6 times 2 over n minus 2 times 2 over n minus 1 times 2 over n. You can see how all of these fractions are less than 1. So let's put this in braces, in brackets. So now what we have is Cn is equal to 2 times 1. Let's factor out this term, 2 over n, times 2 over n, times 2 over third, 2 over 4, 2 over 5, dot, 2 over n minus 2, times 2 over n minus 1. What do you notice about all of this product of these fractions? Every fraction is less than 1. So a product of all these fractions are going to be less than 1. So this is all less than 1. So we can say that Cn is equal to 2 times 2 over n times all of this, 2 over 3, 2 over 4, all the way to 2 over n minus 1, is less than 4 over n. Why are we able to say that? Is because this factor is less than 1. So we have shown that Cn is less than 4 over n, and of course it's larger than 0 because all the terms are positive. So now it's only natural to apply squeezed law. Let's take the limit as n goes to infinity of the expression on the left, which is 0, limit of Cn as n goes to infinity, and limit of 4 over n as n goes to infinity. The expression on the left will approach 0 because limit of 0 is just 0. The expression on the right, 4 over n, will approach 0 as n goes to infinity because the number 4 is just fixed and denominator n just grows out of bound. So 4 over infinity, that's just going to be 0. By squeeze law, the limit of Cn is also 0. Let's write squeeze law. All right. By squeeze law, we have shown that the limit of Cn as n goes to infinity is equal to 0. That means the sequence Cn, and the sequence Cn was, I guess, 2 to the n divided by n factorial. Let me just take a look here. Yes, 2 to the n divided by n factorial. This sequence approaches 0, converges to 0. All right, let's look at part D. So for part D, we have a limit as n goes to infinity of -1 to the n, so dn is equal to limit n goes to infinity of -1 to the n to the 2/3 divided by n to the 2/3 plus 3n. We're also going to apply the squeeze law to this example to solve for the converging limit. The reason is because we have -1 to the n, which is going to be essentially plus or minus 1, depending on whether n is an even integer or an odd integer. So we can basically sandwich in the sequence for which we are trying to find its converging limit. -1 to the n times n to the 2/3 divided by n to the 2/3 plus 3n is less than or equal to, it's going to be less than or equal to -1 to the n. It's going, the most it can be is plus 1, the least it can be is -1. So we get n to the 2/3 divided by n to the 2/3 plus 3n. And -1 raised to an odd power is going to be -1. So we get minus n to the 2/3 divided by n to the 2/3 plus 3n. Now we're going to take the limit as n goes to infinity. So we're going to take limit as n goes to infinity of the expression on the left. We're going to take limit as n goes to infinity of the expression on the right. And then we're going to apply squeeze law to find the limit of the middle expression. Now let's look at the limit as n goes to infinity of -n to the 2/3 divided by n to the 2/3 plus 3n. So our rule is divide by the highest power in the denominator. The dominant term is n, so divide by n, divide by n, and divide by n. And we're going to get minus, subtract the exponents, we get n to the -1/3, which is -1 over n to the 1/3 in the numerator, divided by 1 over n to the 1/3 plus 3. And clearly, when we take the limit as n goes to infinity, -1 over n to the 1/3, that's just going to approach 0, divided by 0 plus 3, then the answer is 0. Similarly, for the same reason, the expression on the right, the limit as n goes to infinity of n to the 2/3 divided by n to the 2/3 plus 3n, dividing by the highest power and taking the limit, this limit is also going to give us 0. So we have shown that this limit, the expression on the right, approaches 0. The expression on the left also approaches 0 as n goes to infinity. So the middle expression for which we are trying to find its converging limit will approach 0 because of squeeze law. All right, so we can say that by squeeze law, limit as n goes to infinity of dn is equal to limit as n goes to infinity of -1 to the n times n to the 2/3 divided by n to the 2/3 plus 3n is equal to 0. Now let's look at part E. For part E, we have limit as n goes to infinity of en. This is equal to limit as n goes to infinity of n minus root of n squared minus 3n. Now, if you look at this pattern, it's going to be infinity minus infinity because inside the root sign, we have n squared minus 3n. That's going to grow to infinity as n goes to infinity. So what do? This is where intuition comes in. Basically, we multiply by the conjugate of n minus root n squared minus 3n, which is n plus root n squared minus 3n. That way we can form a denominator and divide by the highest power in the denominator. So this is one of those questions that you have to have done before to know what to do when you see the question. So that's why it's really important to do lots of practice and lots of homework questions. So let's multiply by the conjugate. the conjugate is n plus root of n squared minus 3n. So we have limit n goes to infinity, n minus root of n squared minus 3n, multiplied by the conjugate with n plus root of n squared minus 3n, divided by the same, n plus root of n squared minus 3n. Simplifying the numerator, we get limit as n goes to infinity of n squared. The radical disappears and the middle terms cancel out. We get minus n squared minus 3n divided by n plus square root of n squared minus 3n. Simplifying the numerator, we get limit n goes to infinity. N squared minus n squared is 0. We just get 3n in the numerator. In the denominator, we just have n plus root of n squared minus 3n. All right, so we have limit as n goes to infinity of 3n divided by n plus square root of n squared minus 3n. How do we evaluate this limit? We divide by the highest power in the denominator, so we're going to divide by n. But to go inside the radical, we have to divide by n squared, divide by n squared, and in the numerator, divide by n. Now take the limit. So we have limit, n goes to infinity, and we just get 3 in the numerator, divided by 1 plus square root of n squared over n squared is 1 minus 3 over n. Let me extend this root just to be accurate here. It's going to be like that. All right. So now we want to take the limit as n goes to infinity. This is going to go to 0, of course. 3 over n is going to go to 0. The result would be 3 divided by 1 plus root of 1 minus 0. That's 3 over 2. The result is 3 over 2. That means the sequence, En, the sequence is equal to n minus root of n squared minus 3n converges to 3/2. All right, thanks.